Hello everyone. I'll tell you a bit about neuroscience here from the illustration standpoint. So I work at the Blue Brain project. The goal is to recreate a digital brain using biologically plausible neurons, astrocytes, vasculature, and all that. At the moment, we're talking about the rodent brain, rat and mouse brain, because the human brain is for later. So I'll tell you a bit about that. Starting with this illustration, it just summarizes the whole project in one illustration that is made of several illustrations I made. You've got at the left EM reconstructions from real brain tissue. Then you've got a neural circuit at the bottom left, where you have neurons reconstructed. Then you have more, a little bit close to the center with NGV, because it's not just about neurons, there's more than neurons. And then you've got simulations on the right, and at the center, topology. And by the way, it's done with Searchock add-on. So I'll tell you a bit about all that. So scientific illustration until nowadays, more or less, was done by hand, and it still is. But science now produces more and more digital data. What does it mean? It means that it has to be consumed with code. Just a reminder for the brain size and all. You've got the human brain and the rat brain. It's not all about size, but bear in mind that we're with the rat brain at the moment, and the Blue Brain says that we've reconstructed 20% of the rat brain. So in 12 years, more or less, it's where we are at the moment. That's what you see in the labs. Well, when you've got nice things to see. One image shows you fluorescent staining of a neuron, and with its synapses revealed, and the other one shows you a slice from the rat brain. And the Nissl staining reveals the core of the neurons that are in there. Now, when I joined the Blue Brain, I joined the visualization team, and it's entirely made of engineers. Engineers, when they visualize stuff, it can be somehow strange because they use full RGB to represent things, and they won't find what the artists do in general. They won't step towards illustration. They will represent data as it is, and that's where I come in, actually. We've got to tell meaningful stories. So when we're given data, to illustrate it is more than visualization. You tell about things like that. Two illustrations that show you one important thing done at the Blue Brain. Blue Brain is driven by data, so they get data, which is this image done here with volumetrics in Blender, and you see a Nissl staining in the background, and then the result is when you populate the regions that you see in the hippocampus with neurons. So we do that. We take that digital data and we put neurons in the appropriate regions, and then we simulate that. Another example is neuroglia vasculature, because I told you about neurons, but it's not all about that. In our gray matter, there are neurons, astrocytes, other glia, and vasculature. Vasculature brings the nutrients, astrocytes take the nutrients, they just grab the vasculature, take nutrients from the vasculature, distribute that to neurons, and they have many regulatory functions to handle the neurons in there. So in these two illustrations, you see real brain tissue reconstruction, and on this part is a digital circuit, a larger scale that we're about to simulate. Illustrations are made for both scientists and lay audience, which means that here you have two images of the same circuit. Here you have the 6 layers represented in the neocortex in a scientific way, let's say more boring, but still it's valid for science. And that is more for a lay audience. That made the cell cover, and it's the same, very much same subject. The neurons are the same in there. And on both images, you see 1,000 neurons. But when I say that this image is for lay audience, it's not just for that, because it helps also show what the scientists do. So it helps them get funding, and overall it serves science as well. So it's not just for the likes of us. Close-up of that, where you see where I worked a lot on the materials with, again, volumetrics, transparencies and all that. It took a while to get there. Now, how do we get to these things? Because you've seen some images, but how do we actually mesh all that? Of course, not by hand. It's not possible. There are millions of neurons and possibly more later. So I experimented with Blender how to represent these things. I went with all sorts of things, so spleens, hair, skin, metaballs, and actually that's what you get from the labs. So under the microscope, they trace points and they represent neurons or cells like that. You have a bunch of points with radius, and you have to do something with that in 3D. So you do that. You try to mesh what you can with that, and you kind of make it realistic again, because if you see the points of the branching, they're a bit rigid, and in reality, the cells are not like that. So you smooth a little bit things, but they have to be correct. They have to match exactly the data that is given. That's another example where you're given a lot of points in the same way as before, and that is blood vessels. You have to imagine that what you're looking at here is maybe 2 millimeters tall. So try to make 2 millimeters with your hand, and that's where you see in there, in your brain. Well, in the rat brain here, but it's also in your brain. To get there, Blender could not mesh such a thing at once. So I had to go with multiprocessing, meshing blocks all together, well, one by one. And then after that, doing something a bit brute force is Boolean merge all that. It's not if an engineer looks at what I do, a person would scream. And I have teammates who have made a better code with other tools to do the same. But it's the work of the scientific illustrator to experiment, to get where nobody has gotten before, and inspire engineers and other people to do the same better. So that's the point of the illustration here. Now, about meshing and all, I tried by all means to mesh neurons, find ways to represent them. And I was also experimenting at home with cycles and saying, well, why not represent things like trees? So I took sapling add-on and generated a few trees and said, why not represent these without meshes? So you go directly to cycles, you give a bunch of splines with their radar, and they're rendered with hair primitives. So there's no mesh. If you look at the vertices, the count of vertices, it's nearly 17,000, and there are almost no triangles in that scene. So it's super fast. And you can apply textures to that, as you can see. So that was an experiment I did at home, and I wasn't really serious because I thought, yeah, it's just an example. But then I got the idea that if neurons look like a bit trees, they share similarities in there, why not apply that to neuroscience as well? And that's what I did. You'll see that just after that. I have to show that it's not perfect. When you give splines to cycles and render them as hair, some bits are missing at the start. You can, again, find the solution by adding points so that they merge with the previous branches. That's what it got to when I tried that with a vasculature data set. And I said, well, it doesn't cost much to try it. And of course, in the center, it's what you see in the viewport. You can't understand really what you're looking at. So you directly go into the preview mode with cycles, and it's quite fast, actually, to preview that. So really, I was surprised with that, and you'll see more hair in the next slides, actually. There were talks talking about going abstract, about animation and all. I also got an abstract result here. It's when you give a certain radius that is so small that then hair goes crazy and it renders strange stuff. So I had also to fix a few things there. By the way, this I didn't mention it was on the slide, but it's a Blender. It's a cycles modification, so you have to recompile cycles with that modification to use it. Neuroscience. When you illustrate it, I found out it's all about extremes. For instance, when you look at this neuron, if you can't see it, it occupies a certain space, but you can barely see its branches. All neurons are like that almost. You barely see them, and there are so many of them. So when you have to illustrate one single neuron, it's even a challenge because your ray tracing will have a difficult time at converging and finding your branches at all. So you go with super large resolution, and that's the only way actually to visualize them. Emptiness is about when you look at Chinese painting, they use negative space to reveal stuff and for our brain to work and complete what we think as emptiness. But the problem is that for Chinese painting, they use that to their advantage as much as they want. The problem with neuroscience is that we're given data and that we don't want that actually. We like to see bigger things, like a sphere is easy to look at, right? It can be small or big. It has a big surface and you can represent it easily. A neuron, even if you invert this image, it's still barely noticeable. Other extremes, when you have the mouse brain, here we talk about mouse brain, there are 865 regions in there. Can you represent them all at once? That was an example of illustration challenge, if you want. And Cycles, again, did a great job there. Also, other extremes, I talked about the blood vessels. Imagine that blood vessels occupy roughly 20% of your brain in the gray matter. The rest is occupied by neurons and astrocytes and glia. So that's only 20% of the volume, actually. A close-up of that. And all the illustrations you've seen so far, they're the result of a lot of coding. So there's maybe 80% of coding versus 20% of creative process there. And the way to get there is actually a way to debug scientific data. So the scientific illustration in this digital era has a key role to play in debugging things, because the scientists that come to you, you visualize it first, and it looks maybe wrong. They go back and fix it. We do another iteration, and sometimes we spot things that were not visible by automated means, because you can do some testing on your code. Let's say there's an algorithm to test something, and you've got sometimes to see things in 3D to understand that there's a major mistake. So that's for the new responsibilities for digital scientific illustrators. There are several to list. For instance, questioning existing scientific illustrations. When you look at that, you do a Google search on synapses. And synapses, they all look like that. But in reality, less than 1%, or even less than that, the synapses are not like that. They're actually like this. It means that there are many branches everywhere in the brain, and it's the connections, the synapses are formed by en passant branches. They come at different places, and when the branches are close enough, there's a branching, there's a synapse that it will form, maybe. So if I get back to that, it looks like there's an end. They say that the end of the axon makes a synapse with another neuron, and it's actually wrong. It should not be represented that way. So questioning existing stuff to not reproduce mistakes of others is important in illustration, because you have a responsibility towards everyone, actually, that you have to tell scientific truth, if possible. Working on materials is one thing where you have an artistic license until the microscopes are good enough to visualize cells so close that you will have to either fake reality or but you will have to reproduce it. Until now, there's no clear representation of what a cell from a close-up looks like. So there, you can experiment as an artist. And in Blender, microdisplacement, UV mapping does help, but it has all to be automated. For the scientific responsibilities, when you do illustration, you have to represent data correctly. So you're given data, and you have to present it as such. And you should not filter things out or remove things or change something because it looks better. Sometimes you would like to do that. You also have to, if you want to add something, to change something that you see, but is too, for the image that you would produce, it would be wrong. You say, okay, when I have a bunch of tubes, I want to smooth them together so that they look more realistic. They have to be based on something that is rather true. So you have to look on the web for scientific papers, and if you want to do something like that, like this cell, here I created what you see. There are spines, the little protruding things in color from that neuron. Their shape is made up because the data that I was given was only the end point and the start point. So I could imagine whatever I wanted to do there. But I had to look up papers, scientific papers, so that these things look correct. And you have to imagine that for every single of these spines, there's a connection with another neuron. So this neuron is connected to up to 10,000 neurons in that circuit. The red things are the boutons. So there's an input to a neuron, an output to a neuron. Input are all the spines, and the boutons are the outputs, actually. Dealing with complexity. Here's another example. When you want to go large scale and you have a lot of cells and a lot of things, how do you represent it? That's an example, a close-up of it, where you see an astrocyte. Astrocytes are territorial cells, and they have their own territories. So they're all sharing space so that they maintain the function of the neurons and distribute nutrients to them. Here the challenge was to illustrate that it's a 3D complicated puzzle, really, and all these cells populate this puzzle. Here I use volumetrics as well as surface rendering. Then that's the second iteration, because on the previous one you only saw the main cell and the neighbors. If you go with another level of neighbors, you get that. And that is more, let's say, artistic, and that won't be used for scientific illustration, really. But it shows that it gets complex really fast. That's the what we get, the full domain of astrocytes in a circuit. And it goes like that then. There's a poster, scientific poster, and we use different illustrations and put them there to represent the neuroglia vasculature. So you see there an example of a poster. These illustrations that are made are also usable as illustrations are standalones. So we make A0 posters like that. We create these illustrations so that we can show them also to the public. And here you see vasculature, blood vessels, and in blue, astrocytes. All these astrocytes that have their own domains. And there you barely see it, but in white are the branches that reach to vasculature and grab vasculature to take nutrients from it. The responsibility for a scientific illustrator for such projects like Blue Brain project is to also inspire people. Because the images that are made, this project are unique. This project is unique, and so you have also the responsibility to sell somehow the project, but also to tell people how amazing the brain is, really. So it's every image you create about the brain is making history, in fact. That's a close-up of the illustration I made recently, where you see neurons in yellow, astrocytes in blue, and vasculature in red. That uses the hair modification of cycles. You see a lot of hair in there, actually. That's the previous one here. Shows you astrocytes in blue, but they're incomplete. They were first version, let's say. Now, if you get closer, you want to better explain what's going on between the astrocyte and the vasculature. And there, Blender helped because I was given data only up to, there's a branch that connects to vasculature, but the part where you see that it wraps around the vasculature is made with a particle simulation in Blender because the data was not given by the scientists. So I was requested to illustrate that. And that's where also you have a certain artistic license where you say, okay, I'll look at what is the average area that this process does when it wraps the vasculature, what is the size of it roughly, and then I do a simulation with that to make an illustration like that. If you want to get down to the molecular level, that's an illustration I did not with Blender, but just to say that we've seen so far just stuff about cellular level. There are a lot of things going on at the molecular level, and there's also a part of the research of the Blue Brain that is trying to depict and model what's going on there. It's a crazy world because when you go to the molecular level, there are millions of molecules everywhere, and if you try to simulate that, we don't have the power to do that. So there are different research scales, let's say, and they all contribute to one to the other. Because when we're too simplified in certain parts, we say, yeah, this neuron behaves like that. Maybe the guys from the molecular research will say, yeah, it's more complex than that. You have to account for this and that in your simulation. That's also one important point for scientific illustrators. When you deal with the digital data, you have to code a lot, but you have not to forget where you want to go. And it's very difficult and painful because when you're an artist, you want to do the art and not spend too much time on the technical part. So it's a kind of a fight trying to bend the tools towards your needs, really. That's an example of the illustration I made with the Sverchok. Even with nodes, when you go with nodes, it can get crazy. So after this project, I said, okay, maybe next time I'll code. It will be faster than using nodes, depending on the project, really. And then going large scale, because so far you've seen illustrations with thousands of cells, maybe 15,000 cells also. But what if you need to go even larger scale than that? Can you do it? Can Blender do it, actually? And that was a challenge. You see here a result where we're inside a large circuit, the isocortex of the mouse brain, the rat brain here. And I'm trying to go to the next slide. Oh, yeah. You see a little bit further from that image you saw before. Ah, it's playing an animation. Okay, it's playing that. Well, you have time to see it. And that's where we get to. So that circuit was created recently. It's 10 million neurons in the isocortex. And the challenge was, can we even visualize that at all? I made it 4 days ago, so it was really the recent thing I did. Here you see 200,000 neurons. Because if you put 10 million, well, first of all, it would not be possible, but you would see nothing at all. So usually for circuits that size, when you visualize 4-5%, it's enough. And here you see a lot of hair, actually. All these neurons are made of, the branches are made of hair, and the cell cores are made of meshes. And this is rendered with cycles. This is another close-up with this time twice as many, because I said, why not 200,000? I could do 400,000. So I said, okay, I'll do that. And this is what you get. When you have 400,000 neurons in one circuit, all the yellow spots are actually the cells that are at the top, and I gave them a special material so that they're revealed. But there are so many neurons below, but it's dark. So at that stage, you could question why even look at 400,000 neurons that way. And this is where there's a certain room to play with materials, with cycles. Can you even go with more neurons? Does it matter to go beyond that? At least so far, so good, I would say. There's only one thing I have to say about that. It took 35 hours just to encode, link all these neurons to the scene. So it started with I tried with 40,000 cells, and it took 20 minutes. And I said, okay, it's fine. It will be done in, if I do 400,000, it'll be done in 10 times as much. But no, 35 hours later, I was still expecting something to happen. So there, I know that Blender is not made for it, but it's still, it made it, because after 35 hours, I got a file. I could open it. I opened it in only 2-3 minutes. And then Cycles took over. Cycles rendered this thing, what you've seen, and it does an amazing job. It doesn't take 35 hours to do a render, actually. It took, for the previous image you see here, yeah, maybe 24 hours, and on a fast computer, yes. That's the last step, actually. When Cycles is working, you're so happy because you're finally going to get the image. So that's about it. Thanks Blender community, because when I started 5 years ago, there was literally nothing for me. When I joined the Blueprint project, I had to almost build my own tools. So I had to code a lot to make that happen. And without Blender, first of all, it would not have been possible. Blender, Cycled, and also the community, because I went a lot on the forums, asking questions and all. Thanks for that, really. It's really, it made my job, actually. And I'll end this presentation with a video. It's a 5-minute video that shows you, I had little time to make it, but it's a video that shows what the Blueprint does from the lab to simulations. And it will be complementary to my explanations here, actually. Thank you. If you have any questions, feel free to come to me. We can have a lot of fun talking about neuroscience.